Welcome. This is one of those topics where the official documentation explains what it does, but doesn't tell you when to actually use it. We're going to fix that. A thread is an independent worker. Your main program is the manager, threads are the staff. Without coordination, they all try to use the coffee machine at once. In this lesson, you'll learn how to start threads safely, protect shared data with mutexes, and avoid the synchronization mistakes that cause real production bugs. Let's get into it. Here's the simplest way to launch a thread. We create a std thread called worker with a lambda that calls doWork. Then we call join to wait for the worker to finish before continuing. This is the bare minimum shape. But there's a problem. If an exception is thrown between creating the thread and calling join, the join never runs. The thread's destructor is called on an unjoined thread, and that calls std terminate. Your program crashes. In modern code, you want ownership and shutdown rules to be explicit. We'll see a better approach in a moment. When multiple threads access the same data, you need synchronization. Here we have a mutex called m and a shared integer total. The add function creates a lock guard, which locks the mutex on construction and unlocks it on destruction. While the lock is held, only one thread at a time can execute +total. The key insight: the lock doesn't protect the variable, it protects the invariant. If several variables must stay in sync, protect the group with one lock rather than sprinkling separate locks around individual reads and writes. One mutex, one invariant, one rule. C++20 introduced jthread, and it solves the join on destruction problem. When a jthread goes out of scope, it automatically requests cancellation and joins. No manual join call needed. In this example, the worker lambda takes a stop token parameter. Inside the loop, we check stop requested. When the jthread is destroyed or its stop is requested, the loop exits cleanly. This is cooperative cancellation. The thread checks whether it should stop rather than being killed forcefully. Jthread makes thread lifetime much easier to reason about. Prefer it over raw std thread for owned worker threads. The producer-consumer pattern is the first concurrency pattern worth learning after plain mutex locking. We have a mutex, a condition variable, a queue, and a done flag. The producer locks the mutex, pushes a value into the queue, then notifies one waiting thread. The consumer acquires a unique lock, then calls cv.wait with a predicate lambda. The predicate checks, is the queue non-empty or is done set to true? The consumer sleeps until the condition variable is notified and the predicate returns true. This pattern introduces sleeping, wake-up conditions, and coordination around shared state. It's the foundation of most real-world concurrent architectures correctly. When should you use atomics versus mutexes? Atomics are right for small shared state, counters, flags, state transitions. A single atomic integer can be incremented by multiple threads without a mutex. It's lock-free and low overhead. But atomics only protect individual operations on individual variables. If you need to update two related variables atomically or protect a larger invariant involving multiple reads and writes, use a mutex. Mutexes are easier to reason about for complex invariants. The rule: atomic for tiny state, mutex for everything else. 4 starting points for your first concurrent design. Shared data structure with a few operations. Start with std mutex. It's simple, well understood, and correct. One producer and one or more consumers. Use a condition variable with a shared queue. The producer pushes, consumers wait and pop. Cancellation-aware background worker. Prefer jthread. It joins on destruction and supports cooperative cancellation through stop token. Tiny shared state like a flag or counter. Consider std atomic. Pick the simplest primitive that fits your access pattern. Deadlocks happen when two or more threads wait for each other to release locks. The classic scenario: thread A holds lock 1 and waits for lock 2. Thread B holds lock 2 and waits for lock 1. Neither can proceed. The fix is simple in principle. If you ever need more than one mutex, define a lock ordering rule early. Always acquire mutexes in the same order. Keep that ordering consistent across all code paths. Many concurrency bugs come from individually correct locks taken in different orders. Document the ordering. Enforce it in code review. This one habit prevents the most common class of deadlock. 3 exercises to build your concurrency intuition. First, take a stood thread example and refactor it to jthread. Add a stop request so the worker exits cleanly on destruction. Second, sketch a queue-based producer-consumer with one producer and 2 consumers. Make sure both consumers wake up and exit when production is done. Third, review a piece of concurrent code and write down exactly which invariant each lock or atomic protects. If you can't name the invariant, the code probably has a bug. For next topics, continue with synchronization primitives for semaphores, barriers, and latches. Then, advanced ranges and views for composable, lazy sequence operations. You now understand the fundamentals of safe concurrency. Build on them carefully. Thank you.